Hello and welcome back to today's videos. In this video, we're going to discuss local minima and maxima of functions and how to find them if a function is differentiable. So this section is simply called local minima and maxima. First, of course, we'll have to define what precisely we mean by a local minimum or a local maximum. And as usual, we do this for functions defined on an interval because that is the setup that we need for our differentiable functions. So let I subset of R be an interval and f I to R a function on I. Then the first thing we need to define is totally independent of the function. We'll define what we mean by a neighborhood. Basically, the idea is if we have a point in the interval, then we want to compare the value of the function at that point to the values in the immediate vicinity of that point. So a neighborhood is basically a small interval around a point, and we can make it as small as we want it to be. How small that is will be dictated by a parameter. We call that delta. So for delta, strictly greater than 0. And of course, we also need the point where the neighborhood is centered. So a point x star in I. The interval, and we'll denote that as n delta of x star, and that will be an open interval with boundary points x star minus delta and x star plus delta. So we just move from x star a little to the left and a little to the right. And this will be called the delta neighborhood of x star. And I will simply say, to define a local minimum or maximum, what we do is we look at the point and then identify a neighborhood that is small enough such that the point is the one with the largest or the lowest function value for all points in that neighborhood. And if there is such a neighborhood, then we'll call a point a local maximizer or minimizer, and the function value a local minimum or maximum. So this is basically the rest of this definition. We'll start with maximizers. So part 2, a point x star in I is called a local maximizer of f. And the function value at that point, f of x star, is then called a local maximum of f if there is a delta that is strictly greater than 0 such that the function value of all points x in that neighborhood is less or equal to the function value at x star. So this needs to hold for all x in the neighborhood and of course also in the domain. So the function needs to be defined in order to be evaluated. So we'll require this for all x in I intersected with the delta neighborhood of x star. And please note that this also works for boundary points. For example, let's say we have a function that looks like this here. And we want that on the interval from 0 to that point. So this is our interval. And let's say that's a closed interval. So that point might still be part of the function, and that as well. Then, of course, a neighborhood of that point here. That reaches to both sides, right? So this is a delta neighborhood. And then we want this criterion to be applied for all points that are inside the actual domain, the interval that we're looking at. So what we do is we restrict our neighborhood basically to just these points here. And then we can say that point is actually a local maximizer or a local maximum here, because we don't have to care about the points on the right of that. It's a boundary point after all. So this also applies to boundary points. So this here is a local maximum. And this point here, that would then be a local maximizer. And of course, the same idea works for interior points, points inside of that interval as well. In this case, you have to consider both sides, left and the right of that point x star. Okay, so that definition is general enough to also apply it to boundary points. And of course, what works for maximizers and maxima will also work for minimizers and minima. So the third part is a point x star in I is called a local minimizer of f, and consequently f of x star a local minimum of f. Again, if there is a delta greater than 0 such that in this case we want f of x to be greater or equal to f of x star for all x that are in I and also in that neighborhood. And again, you can make that neighborhood arbitrarily small. So just make it small enough. It's sufficient if there is such a neighborhood. And finally, part 4, there will also be a general name for minima and maxima. We'll just speak of extreme points or extrema. And that is part 4, a point x star in I is called a local or possibly global, if that's the case. So we already defined global minima and maxima. And generally a maxima or a minimum, maximum or a minimum will be called an extreme point. Or just, again, local or global extremum. Of f if x star is a local or global maximizer or minimizer. So that is the definition of maxima, minima, maximizer, minimizer. Now the question is, of course, how can we find local extreme points for differentiable functions using the information that the derivative gives us? And this is what we'll investigate in the following. So let's say we have a differentiable function. consider a differentiable function. We call this function f. Let it be defined on an open interval I. As usual, subset of the real numbers. And let's say we have a local maximizer. We'll just do this for the maximizer. The minimizer works in the same way. So we have some local maximizer x star. Then that means there is a suitable delta neighborhood. Let's say we call that suitable delta star, such that let's just assume the interval is open, so the point x star cannot be a boundary point, and that means there's always a neighborhood that is completely included in that interval as well. So we can assume delta star is chosen suitably, such that x star minus delta and x star plus delta, this open interval here, is completely included in I, and such that now the maximum and minimum condition, we'll express this in a little different way. What we say is that for every delta between minus delta star and plus delta star, we have the following. So as long as we move less than delta star away from x star, we get f of x star plus delta is less or equal to f of x star. Remember, x star is a maximizer, so moving away from x star by this amount delta will give us no higher function value, as long as we stay within the delta neighborhood, the delta star neighborhood here. Okay, so this is what is given. And well, what does that mean? That implies, of course, that if we take the difference of those two, f of x star plus delta minus f of x star, now this will usually be less or equal to 0. And if we then divide this by delta, and let's assume delta is positive, so we will exclude 0 from this investigation here for the moment. If we then divide this by delta, then there's two possibilities. If delta is positive, then this division doesn't change the sign, so this here being less or equal to 0, the whole thing is still less or equal to 0. On the other hand, if we divide an inequality by something negative, then the inequality sign flips. So if delta is negative, then instead of less or equal to 0, we'll get a greater or equal to 0. And now this thing here, that should look familiar. We do know that f is differentiable. So what we can do is we can take the limit of this expression as delta tends to 0. And this is defined and is equal to the differential, the derivative of f at the point x star. So as f is differentiable, the limit of this expression for delta to 0, f of x star plus delta minus f of x star divided by delta exists and is equal to, well, just the derivative of f at the point x star. On the other hand, if we consider the one-sided limits, then we know those must agree. So the limits of delta to 0 from below of f of x star plus delta minus f of x star divided by delta, and the limit delta to 0 from above of the same expression. Those do exist and they also agree. And again, we know that this expression here for positive delta, this expression is less or equal to 0. Positive delta is this case here, so delta approaches 0 from above. That means this expression is less or equal to 0. And in this case, delta approaches 0 from below. We know that this expression is greater or equal to 0. So what we have here is a limit that must agree. One of those needs to be less or equal to 0. The other needs to be greater or equal to 0. So the only possibility that those can agree is if f prime of x star is both less or equal to 0 and greater or equal to 0, because they both tend to the same value. And of course that means f prime of x star must be equal to 0. So what we have just concluded is that if we have a local maximizer, then necessarily the derivative at that point must be equal to 0. And of course we can do the same thing for local minimizers. The result will just be the same. So let's write this down as the central theorem here of this section. And that theorem is often called a first order condition for local extreme points. First order condition because it involves the first order derivative. And this condition is easily formulated. So as usual, we have an interval I subset of R, let that be an open interval. And let f be defined on that open interval and differentiable. Then if x star in I is a local extreme point, then f prime at x star is 0. That's the condition here. So in other words, if you want to find the local extreme points, we can limit the possible candidates to all those points where f prime is 0. On the other hand, not all of these points need to be local extreme points. That is not implied by that theorem and is not true in general. So f prime of 0 is a necessary condition for a local extreme point. All extreme points will fulfill this, but not sufficient, meaning there might be points where f prime of x star is 0, but the points need not be local extreme points. And to make things a little easier, those points where f prime of x star is 0, those will get a name because we'll often refer to those. Those points will be called stationary points. So let's quickly define that. Let's say that I be a subset of R, be an open interval, and f a function on I that is differentiable. And then we call a point x star in I with f prime of x star equals 0. We'll call that a stationary point of f. So basically, if we want to find extrema, local extrema, we first have to find all stationary points. Now let's have a look at a quick example to see what we can do here. What we're going to do is we're going to consider the function f of x equals 2x to the power of 3 minus 9x to the power of 2 plus 6x plus 20. Then we'll have a look at the derivative of that function. First order derivative, that is 6x squared minus 18x plus 6. Or you can factor out the 6 here and we get 6 times x squared minus 3x plus 1. Now let's find the stationary points of f. And to do that, we have to find the points where f prime is 0. And that is true if and only if x squared minus 3x plus 1 is 0. Now that's a quadratic equation, and the roots of that equation are easily found by just applying the formula. So x1 and 2, the two roots of that quadratic equation are 3 plus minus the square root of 3 squared, that is 9, minus 4 times 1 times 1, so minus 4, divided by 2. So what we get is 3 plus or minus the square root of 5 over 2. And that means stationary points. Let's order those such that the first one is the lower. So we have x1, which is equal to 3 minus the square root of 5 over 2. And we have x2, which is equal to 3 plus the square root of 5 over 2. Now obviously those are the only extreme points, and we have x1 is strictly less than x2. These are the only stationary points, and we have x1 is less than x2. So f prime can only change sign at these points, and that means those are the only candidates for extreme points. So we have these two candidates for local extrema. And of course the question is now, are these actually local extrema, and of which type? Would they be local minima or would they be local maxima? And to find that out, we look at the monotonicity of f. So we want to classify those. Classify those possible extrema through monotonicity. So basically what we need to do is we need to find out whether a function is increasing or decreasing before and between those two extreme points. So the first thing we do is we'll have a look at the 2 points in particular, and what we see here is that this x1, 3 minus the square root of 5. The square root of 5 is still less than the square root of 9, which would be 3, and for the square root of 9 we would get 3 minus 3 over 2, that is 0. So we can be sure that this expression is still positive. So 0 is actually less than x1. Okay, on the other hand, what about 2, x2? How large is that possibly? So we want to find a point that is beyond x2, so to say. And again, the easiest way would be if we increase this 5 here to a number that we can actually compute the square root easily, like 9, then that sure is a number that is higher. And if we increase that to 9, then we get 3 plus 3 over 2. So that is 3, and that means x2 is less than 3 for sure. And finally, we need to find a point that is in between those two. And one possible point in between those two would be, for example, if we just increase that, decrease that until they meet. And for example, we could say if we do not subtract 5 but nothing, 0, and do not add 5 but instead nothing, 0, then we make x1 higher and we make x2 lower, so we meet somewhere in the middle at 3/2. So what we can be sure of is that 3/2 is included in this interval between x1 and x2. So those are the points that we are going to investigate. And we know f prime can only change sign at the two stationary points. So if we find a point left of x1, then and determine the sign of f prime left of x1, then that will not be able to change anymore as long as we do not cross x1. So that means what we have here is f prime of 0. That is, well, remember f prime, well, let me write that down once more. F prime of x is 6 x squared minus 3x plus 1. So f prime of 0 is simply 6, and that is of course positive. So that means the function is going to be increasing to the left of x1. So f is increasing in this interval from minus infinity to x1. It'll be stationary at x1. Now what about in between x1 and x2? So to find that out, again, we'll take one point in between that interval, and then we know the sign of f in that interval as the sign can't change. There's no roots, and the function is continuous. So f prime of 3/2, let's evaluate that. That is 6 times, let's see, x squared is 9/4 minus 3 times x, that would be 9/2 plus 1. So what do we get here? 9/4 minus 9/2, that is minus 9/4. 9/4 is strictly greater than 1, so plus 1 will still not get us positive. And that means this is less than 0. And what that means is f is decreasing in the interval between x1 and x2. And finally, let's have a look at a point that is beyond x2 as well. And we already said 3 is one such point. So we try to evaluate f prime at 3. And if we do that, we get 6 times, well, 3 squared is 9, minus 3 times 3 is 9 plus 1. So we're left with 6. And that is positive. So f is increasing in the interval from x2 to infinity. Okay, as I said already, notice that f prime is continuous on R. So it cannot change its sign at points other than the stationary points. Okay, so we have a continuously differentiable function here. And well, what does that mean? Let's summarize the results that we found so far. What that means is that in the interval from minus infinity to x1, we have a function that is increasing. There's this point here. So the function rises like this. Then we have the point x1 here. Then we have the interval from x1 to x2, and we already said in this interval here from x1 to x2, the function is decreasing. So it behaves like this. Then we have the point x2, and then the interval from x2 to infinity, and we found out that the function is increasing in that interval. So let's write that down. The function is increasing here. So it behaves like this. Well, what that means is if a function is increasing and then decreasing, of course, the point here in the middle must be a local maximum. And if it's decreasing and then increasing, the point here where it changes must be a local minimum. So this is the results that we infer here. So this is going to be a local maximum, and this is going to be a local minimum. Right? So basically, the function looks something like this. It's increasing up to x1, then it's decreasing up to x2. So this here is x2, this here is x1, this is a local maximum, this is a local minimum. That is the local behavior of our function f. And so through stationary points and monotonicity, we can classify the behavior at the points, and we can find out whether a point is a local minimum or a local maximum, or also nothing of that sort. If a function is increasing before a stationary point and increasing afterwards, then of course we will also have found out that this is surely not a local extremum or similar things. Of course, as you have seen, this monotonicity thing is quite hard work, so we would like to have a criterion that is a little simpler than that. And indeed, there are functions where we have such a criterion, and we'll discuss this in one of the upcoming videos. I'll see you then.